Well, that was quite a first session. All those applications and huge bandwidth demands and the scaling of the internet. My name's Ted Rappaport. I'll be talking a little bit, but I wanted to introduce our moderator for this session, which is how are we going to do all those things with the internet? How are we going to provide that bandwidth? And a look at the core and the edge of the future internet. Andy Chraplyvy, Vice President of Research at Bell Labs, Optical Networking, and a Marconi Fellow, has put together the session. And I'll invite Andy up now to talk more about the rules of the road for this session.
Thanks, Ted. He wasn't totally forthcoming. Ted actually did the bulk of the work of organizing this session, and I was called in to moderate it because Ted, as you know, is also a speaker in this session, and from what I've been told, he rarely keeps to his time limit, and so I'm called here to ride herd on Ted specifically. Thus far you've heard from what we affectionately call the gee whiz crowd, and they've told you about all these marvelous new applications and things that you have to look forward to as the internet evolves and grows. The second session is going to be what I call the realist crowd. So the first session, they gave you all these great visionary things with total disregard about the issues of resources like bandwidth, capacity, and energy. And this session is going to address some of these problems. And I think that you'll find it particularly interesting because some preconceived notions that you might have are simply not true. And one of them being, for example, that the capacity of optical fibers is nearly limitless. And you're going to get some sobering indications of that we're reaching the end of the road. So there will be two talks on fiber capacity issues and bandwidth issues, and then two talks on the wireless end of things. So the first speaker was going to be Bob Koch, who will talk about optical fiber capacity from glut to scarcity. And this will be followed by Peter Windsor, A New Era in Optical Networking, Spatial Multiplexing, and Optical MIMO. I like to call it the last frontier of lightwave communications, and you'll see why from Peter's talk. Then we'll switch gears, and we'll try to keep Ted to 15 minutes on sub-terahertz wireless communications, the future edge of the internet. And again, no introduction needed for Vint. He'll address some of the energy issues that we're going to have to confront, and that's a talk titled by Power Awareness in a Mobile Environment. So let's kick it off with Bob Koch that's going to scare you about fiber capacity.
Thank you. Let's see, how do I do this? Looks like this one. Great. So I want to talk about, as Andy said, about the infrastructure of the internet, in particular sort of a core network infrastructure, how you get the bits across the large distances. And I'll talk a little bit about traffic at the beginning. Since this all started, the traffic has been growing and doubling every 1 to 2 years for a long time. And that hasn't really, if you look at it, it's not really dependent on particular applications. The applications come and go, but this rate of growth has gone on. And I'll try to talk a little bit about why I think that is. And then I'm going to try to look at this in the context of the development of capacity of the core network infrastructure, optical fiber communications that we use. And in particular, wavelength multiplexing really enabled tremendous growth of the capacity of optical communications and created this notion that the capacity of fibers is limitless. And we have seen something very dramatic happen in the last few years that hasn't been noticed necessarily by the people who actually use bandwidth, but by those who provide it. We've gone through a very dramatic transition, and I'll try to illustrate that for you. So here's some information about traffic in the internet over the period from 1980 to 2020. And you can see that the growth rate is relatively stable on there. That line that's drawn through there is at 2 dB per year. So if we were talking about 100 years, it'd be 200 dB increase in traffic. Luckily, we're not talking about 100 years today. But 2 dB per year, 10 years, that's a factor of 100. That's a really serious growth rate. And you can see from the mid-90s forward, that line is not a bad fit. I mean, we can quibble about it, but if we start talking about dBs per year, it's around 2. So why does that data traffic keep growing? And because you saw that relatively smooth growth rate, even though we know that many different things have been supporting that growth rate over that time. Initially, something just like email, lately, video streaming, peer-to-peer was the big thing at one point. but you don't really see those individual applications coming in there. And I think the reason for that is that, of course, no matter what, the traffic is going between machines, and those machines are on a growth rate that has actually been very stable, this sort of doubling every 1 to 2 years of the number of transistors, the rate at which data can happen. And also, if you just look at the amount of data that exists out there, the amount of data that's stored, that's growing at a rate. And I'll show you some pictures of that stuff in a moment. So for instance, for computers, for every instruction per second, it needs about a byte of memory and a bit per second of I/O. So that's something that you'd believe anyway. If I make the computer twice as fast, probably the pipes in and out are going to be twice as fast. There's no big surprise. And as we start to do things like cloud computing, the data transmission in the internet starts to be more like the data transmission inside the machines themselves. So here's the top 500 supercomputers, and it tells you how the processing has been growing. And those lines are pretty straight. It's surprising, and that's 2.5 dB per year, so very close to this 2 dB per year traffic growth that we were talking about. And you might say, well, what do supercomputers have to do with everyday computers? Here's a collection of processors. Just every microprocessor somebody could find, they put these points on here over the years. And I drew the line through the bottom end, sort of the low-end processors. And you see that's also sitting at 2 dB per year. And this is essentially just a manifestation of Moore's law. So I'm arguing basically that it's really this fundamental progress of technology that's driving traffic. And the applications are really what technology enables us to do. Applications come and fill it as we have the ability to do them. Let's look at it from the point of view of data. If I have content there, if I have stuff that's stored, it has to be communicated, even if all I'm doing is backing it up. If I'm taking sites and I mirror them one place, and then some fraction of that data has to be moved. If I double the amount of data, I double the traffic. And if you look at this growth rate, this is from a report commissioned by EMC. You see that the total amount of data they call the digital universe has increased 10 times in 5 years, or 2 dB per year. So these things, it's a pretty strong argument that this is really what's happening. This is what's driving things. And all these things are related together. And that's why the traffic keeps growing at about 2 dB per year. So let's look at the supply side in terms of bandwidth demand. This is a picture of research capacity demonstrations for single optical fibers as a function of year. The blue dots were before we had WDM, and then the red squares are when we started doing wavelength multiplexing. We started using multiple colors on the fiber. So you see a couple of technologies, and they both have this sort of curving over appearance. And it's, when you start to use a technology, you can very easily adapt things. For instance, in wavelength multiplexing, you have one wavelength, you put 2, so well, I can do 4, I can do 8. It's very simple until you use up the bandwidth. That's what that very sharp kink in the curve is. When we had put as many channels as we could fit in the optical bandwidth we had available via amplifiers, the only thing to do then was to start using them more efficiently, pack them more closely together, increase the spectral efficiency, and the rate of increase became much slower. This chart shows the rate of increase of spectral efficiency in optical communications from 1990, after you see that kink forward. And various things came in to do this, going from just getting the channels packed more closely, getting the filters more rectangular and so on, to now using QPSK instead of just a binary format. And the net rate of growth of spectral efficiency we've been able to achieve is about 1 dB per year. So about half the rate of the growth of traffic. So this line is already falling behind the traffic growth. And it's hard to see how you get the spectral efficiency to 100. We're at about 10 now, 10 bits per second per hertz in research demonstrations. That's a very efficient use of spectrum, especially in optics, where we were mainly used to 1/100th of a bit per second per hertz in the early days of the technology. So this is that same picture again. I want to now translate and think about commercial things. These are the commercial systems that were introduced using these same technologies. And you see a shift of the curve over by about 5 years or so. The commercial systems have followed the research systems, as you might expect. So this next chart, I'm going to look now at the traffic again, only I'm going to put the voice traffic on the plot as well. So we have voice traffic and then data traffic, the 50% per year data traffic there. And that composite curve now shows on this curve where I've superimposed data traffic and commercial system capacity in a single fiber. And you can see that there were two remarkable years, 2000 and 2008. In 2000, the capacity of a single fiber crashed right through the total data traffic in the network. You could carry all the traffic in the network on a single fiber. And that is when everybody realized, oh my gosh, we have a tremendous glut. Everybody put in one good fiber system, and they didn't need another one for quite a while because they were able to carry all the traffic you could need. In 2008, we crashed through the curves in the other direction. The network traffic is on a much steeper slope, and so those are actual introduced systems. The most recent one introduced in 2011 is 100 gigabit per second channels on 50 gigahertz spacing, spectral efficiency of 2 in commercial systems. And you can see that now, and from here on, we're falling behind at a factor of 10 every 10 years in terms of traffic versus system capacity. So this is just a look at interface rates for just for a little balance. You can see various interface rates for transmission systems. WDM are the blue squares, for instance. The red things are things like cross connects, back when people used to do a lot of grooming in the digital domain. And then the green triangles are for IP routers and the interface rates on those routers. You see the dramatic thing that happened in 2000 at 10 gigabits per second. We started to have 10 gigabit interfaces on routers and 10 gigabit wavelengths, and there wasn't a lot of room for other grooming. And that stayed in lockstep through 40 gigabits and 100 gigabits per second. So the interesting thing is to push that out to 2020. What do we expect that interface rate is? It's a terabit per second. And it isn't really obvious how we extend where we are now to a terabit per second. So a state-of-the-art system today is polarization multiplex. So we use both polarizations of light with QPSK, so we get 4 bits per second per symbol at 28 gigabaud for 100 gigabit per second channels. We use coherent detection to do all of that, and digital signal processing to enable us to take out all the impairments, go about 1,500 to 2,000 kilometers. But now that next step, that 10 years, just to stay on the curve that falls behind the traffic by a factor of 10, means we need 1 terabit per second channels at 20 bits per second per hertz. And those are numbers that we just really don't see how we would achieve. You could imagine, well, we're using QPSK, as I show in the first constellation there. We could just go up in complexity of the constellations. And these are all done at more or less the same average power for the constellation. You can see what the problem is. As I go up in constellation complexity, the signal-to-noise ratio needed becomes much more dramatic. And this chart shows how far can I make such a system reach. If I keep the bit rate constant, I keep the power constant, and I just change the constellation, so I'm making it more efficient. Here's BPSK, QPS, polarization mux BPSK, QPSK. Those are all essentially the same. You get that all for free. I go to 16 QAM. I went from 1,000 kilometers down to 400 kilometers. I could imagine maybe 400 kilometers will be enough. Maybe I can stretch that one and make it work. Oops, I'm sorry. Well, the next one at 64 QAM is so bad that it's really not useful for core network applications. So now let's look at it from a fundamental perspective. What do we think we could do? And the Shannon capacity of a channel is given up there. And we'll see that, of course, that logarithm is really a tremendous problem. Signal-to-noise ratio is what we have a handle on. We make it better. Things only get better by the log. So that's the fundamental Shannon curve. Signal-to-noise ratio is only improved by increasing the power in an optical communication system because the noise is a fundamental property of the amplifiers. And as we increase the power, at some point, fiber nonlinearity comes and turns the capacity curve over. And this chart shows some actual calculations of the capacity based as impacted by nonlinearity. And you show that the capacity will turn over under these assumptions, about a 500 kilometer system in single mode fiber at something like 9 bits per second per hertz. And the recent experimental results are shown down there, the systems at about 500 kilometers getting to about 3.5 to 4 bits per second per hertz. So we're something like 2 to 3 times away from what we believe is a nonlinear Shannon limit in single mode optical fibers. It isn't clear how we would get around that. You could imagine that I might increase or decrease the loss of fiber, improve the fiber, say. If I do that by, say, well, let me put a slide up. If I change the red star is where we are today, and you have that sort of 8 to 9 bits per second per hertz. If I take that fiber loss and decrease it by a factor of 10, I'll get to 11 or 12 bits per second per hertz. I'm not going to decrease the loss of fiber by a factor of 10. That's simply not going to happen. So, and I can imagine increasing other parameters, improving signal-to-noise ratio of amplifiers a little bit, or I can imagine decreasing the nonlinear coefficient of fiber. All of those parameters are moving me on a curve like this, where I'm seeing this very poor logarithmic improvement. And once I have a reasonable spectral efficiency, it's very, very hard to multiply it by any decent factor. So traffic is growing much faster than system capacity. The current capacity growth rate, as lamentably slow as it is relative to the traffic, will be limited by fiber nonlinearity, not so far from where we are today. And what we need is some kind of new version of WDM, something that will give us that chance to go up on the vertical slope for capacity increases, that just tweaking and improving the current technology will not allow. Thank you for your attention.
All right, good morning. I will basically continue with Bob's talk and say what we're doing right now to solve that capacity problem. This is another version of what Bob showed us, just plotted here the transmission distance and achievable spectral efficiency. Here you see the nonlinear Shannon limit, as Bob showed. And here you see all these experiments, and that's the factor of 2 that we are away from Shannon at around 1,500 kilometers, which is a reasonable transmission distance. Now let's look at the systems. As Bob said, current systems have about 100 channels at 100 gigabits per second, and they work at 2 bits per second per hertz. Now with 2 dB per year, we should be about systems that can do this in 2016, which is clearly beyond the nonlinear Shannon limit. And that's for products. That's not research. That's for products. Now, what can we do to overcome that? If you look at the physical dimensions that we have time to send the symbols. We have the quadrature space for bandpass signals, I and Q components, and we can go up in spectral efficiency by using higher order modulation. And I'll talk about that later too. We have the frequency space by doing WDM, and we have polarization, which gives us another factor of 2 through polarization multiplexing. But all of these physical dimensions are already in use by products, not just in research, by commercially available optical transmission products. So the only physical dimension that I'm aware of that we still have to exploit is space. And the good thing about that is that this is an exhaustive list to my knowledge. So there is no other way. We know that we have to go space. There is just no other option. What we'll do once we have exhausted space, that's another question, but that's 10 or 20 years out. So let's worry about that later. Let's worry about that for now. So spatial multiplexing or space division multiplexing could mean anything as mundane from using several fibers in a single cable. That's a form of spatial multiplexing. Or you can integrate those fibers into multi-core fibers like that, or even into multi-mode or few-mode fibers like that, where you send different information on different modes supported by the waveguide. And we've looked at all of these, and we'll talk about those. But first, let's look at the value proposition. What do you gain by using spatial multiplexing as opposed to shortening the regeneration distance and just cranking up the modulation constellation size? So these two systems have the same spectral efficiency. It's 64 QAM, so that's 6 bits per symbol. And this is 3 times QPSK, so 3 times 2 bits per symbol. So they carry the same amount of data over the same distance. Only difference, here you go transparent, whereas here you have to use multiple regenerators. Now, if we look again at our transmission distance and spectral efficiency plot, and we start from today's experimental baseline, if we want, at a certain spectral efficiency, if we want to go 3 times the distance, we just concatenate 3 spans. That's what we have to do. So that gives us this point here, a longer distance at the same spectral efficiency, and here we need 3 transponder pairs to do that, because we need all these intermediate regenerators. If we go spatial multiplexing, we multiply up the spectral efficiency at a given distance. So if I use 3 paths, I have 3 times the spectral efficiency at the same transmission distance. So I multiply up in that direction. Now you can already see what happens. If I superimpose these curves and pick some target value here, for example, then to reach that target value of 20 bits per second per hertz over 1,500 kilometers, I'd need 300 regenerators if I were to crank up the constellation, whereas I just need 3 spatial paths, and I still have room to grow. So that's very clear what you should do. So from a value proposition point of view, it's very clear that going to extremely high order modulations is just not what you should be doing. So let's look at another thing, and that's integration. If you just deploy m spatial paths, then you get m times the capacity at m times the cost, m times the energy consumption. So the cost per bit, the energy per bit stays constant. That's not a scalable solution, because that means that the transport cost and energy consumption would grow by more than 1 dB per year if you take into account already the natural decrease in per channel energy and cost reduction that occurs through price erosion and better systems. The key to making all this work is integration. Integration at all levels. You need integration on the transponder side, integration on the optical amplifier side, and integration on the fiber side to shrink everything, to integrate everything, to make sure that the energy per bit and cost per bit keeps going down. Now, this is an example that Chris Durr at Bell Labs showed a 7-core fiber transponder. It's a receiver that's fully integrated and can be coupled to a 7-core fiber and simultaneously receives 7 signals from those 7 cores, polarization multiplexed already. That's another example. What we recently did, a 7-core fiber transmission experiment where we did 112 terabits per second over 7-core fiber. And that was achieved by just using QPSK, so a very simple modulation format that's very robust, can go very long distances. I mean, we only did 77 kilometers here because we didn't have enough fiber or the possibility to loop at this point. But this is scalable to thousands of kilometers. Now, let's look at space division multiplexing in the bigger context here of WDM. That's essentially the same what Bob showed. The single channel rates growing at half a dB per year. WDM initially growing at 2.5 dB per year, then slowing down to about 0.8 or 1 dB per year, and going at the same slope as single channel. And now we need some technology that brings us back up there into the petabit per second capacity for transmission. And this data point here is the 112 terabit point for 7-core fiber that we just saw on the last slide. So this is already reality. We are having spatially multiplexed transmission experiments that already outperform the best single mode experiment that has been shown. So we really need to climb that curve, and that will be the topic of the future. Now, integration fundamentally introduces crosstalk. As soon as you integrate too much, you'll get crosstalk. Now, the impact of crosstalk depends on which modulation format you're using. These 64 QAM, higher order QAM constellations are much more susceptible to crosstalk. So you want to look at what crosstalk can I accept and then build a modulation format around that. But then the question is, can you even get to, say, 20 dB of crosstalk over 1,500 kilometers? Can you even do that with integration? So if you cannot, there is a very good technique available, that's MIMO, and very well known in wireless and used all over the place. And MIMO is the way to go if you want to suppress crosstalk or to undo crosstalk. So one important thing here is that MIMO is not equal to MIMO. So in wireless, there are a lot of different boundary conditions than you have in optics that relate to MIMO technologies, and some of them are listed here. So in optics, you have the possibility to address all waveguide modes. The complete orthonormal set of modes is available to you to address and to receive. That's different to wireless. Another difference is the high reliability requirements. We have this 5/9 reliability or low outage requirement. It's not like 10% or 1%. We need 99.999% of reliability. Otherwise, a massive amounts of data that you carry across the continents, that's not going to work without this reliability. You can't just retransmit that amount of data. You have distributed noise due to inline optical amplifiers. You just don't have your noise loading at the receiver. Then receiver to transmitter feedback is almost impossible because of the long round trip delays over 1,500 kilometers or even 10,000 kilometers. Fiber nonlinearity, and that's the most fundamental thing. Even every spatial multiplexed fiber will eventually be nonlinear, which puts nonlinear constraints on the MIMO processing. And as far as I know, MIMO has been considered in a linear regime mostly. So there is a lot to be done to extend MIMO to the nonlinear fiber channel. That's probably the key challenge here. So that's an experiment that shows multi-mode transmission in a special 3-mode fiber. So that's a fiber that just supports the LP01 mode and the LP11 mode. It's twofold degenerate, and then it has 2 polarizations. So it's a 6x6 MIMO experiment. And what we did here is we designed a special coupler that is able to excite individually and selectively, excite each and every of these 6 modes. Then you have this fiber where you have crazy mode mixing going on, so it's a very bad channel in that sense. And then you use a spatial multiplexing demultiplexer to read and detect these modes, and then you use MIMO processing to recover the data. So that's this MIMO equalizer. It's an adaptive equalizer, a 6x6 matrix of impulse responses that each has around 100 taps, each of these filters. And if you do that, do the digital signal processing, you get very good performance. So you have here the back-to-back and here the transmission performance with very low penalties. And that's, of course, all offline process. So we grab the data onto a computer and then do MATLAB to process it. But it's real measured data. It's not simulated data. That's just a glimpse in the lab. So you really need a lot of equipment to do this because you need to capture 6 high-speed channels so that you have 1, 2, 3, 4, 5, 6 channels. So just what you see here is over $2 million. So it's a huge investment that needs to be taken to make this reality. Okay, and as a conclusion, I just want to pull up that figure. I mean, there is a lot to do. That's the exciting thing right now in optical communications research. It's a wide and open field, and there is lots of exciting research ahead of us. We don't know how to build the right fibers, how to build the right amplifiers, how to interface to chips, how to do the processing, how to build ROADMs, like optical routing nodes. So there is plenty of work to be done. Thanks.
Okay, well, while Peter and Bob make the backbone of the network able to handle tens or hundreds of terabits per second, I'm going to take a look at the wireless world and what's happening in wireless to try to get the data rates up to be able to handle the applications that Erwin and Vint and Tom showed us for high bandwidth. And it's pretty remarkable when you look at the wireless industry and you look at the history of mobile radio and even Wi-Fi, starting from the days of Marconi at the very top of the top graph from 30 kilohertz to 300 kilohertz, and then AM radios in the 300 kilohertz to 3 megahertz segment, and then moving to FM and cellular radio in the 450 and 900 megahertz bands. You can see in orange the cellular, and then to Wi-Fi at 2.4 and 5 gigahertz. The fact is that over the history of the world, with every wireless application on the planet, if you put all the bandwidth together back to back, that bandwidth is still less than an exciting new band that is just starting to become commercialized around the world at 60 gigahertz. In 1995, the FCC opened up 7 gigahertz of spectrum at the 60 gigahertz carrier frequency. You can see it on the bottom. And that little circle at around 60 gigahertz is the spectrum available unlicensed, which is greater than all the shaded area on all the wireless systems before. Other governments around the world have since followed suit, and so what you have right now across the globe is an unlicensed spectrum with several gigahertz of common bandwidth available for data rates that we've never contemplated before. The other thing that's very exciting that's led to this, and this is the role of governments such as the FCC, is to provide those spectrum allocations that allow us to create the new products that'll impact the next generation. It was the ISM band at 900 megahertz to 5 gigahertz in 1985 that allowed spread spectrum to move from satellite and government applications into the consumer world. And of course, it's great being in the home of the founding of spread spectrum and for CDMA for cellular here in San Diego. But the CMOS research activity, transistor research over the last decade has moved the capability of semiconductors far above 60 gigahertz. And this is why 60 gigahertz will be commercialized this year, and you'll hear a lot about it over the next 2 years. But this is the tip of the iceberg, because semiconductor capabilities led by digital, but now also analog, are allowing us to start thinking about wireless devices at the sub-terahertz regime with carrier frequencies of 100, 200 gigahertz or more, made possible by Moore's law. And as you get up to these higher and higher frequencies, the wavelengths become small, so small, on the order of millimeters, the size of a freckle on a human body, that you start to realize that future wireless devices are going to have completely different form factors than we've had. So if you look at the spectrum from 60 gigahertz and above, what you see is that there are these natural bands created by the atmospheric absorption where there's high attenuation and low attenuation. For example, the 60 gigahertz band was viewed as a safe allocation in the mid-90s because there's 10 to 20 dB of attenuation per kilometer. So the interference won't be great. No matter what your power level is, it'll dampen out quickly. Yet there are other bands at the, for example, at the 77 gigahertz for vehicle radar today and 230, 240 gigahertz band, 90 gigahertz, where there's very, very low attenuation. So you can start thinking about fifth generation cellular, mobile radio devices that will be able to operate at these frequencies and take advantage of the very small wavelengths to create the future mobile devices that will exploit directional antennas and create long distance, over a kilometer, cellular, mobile, high-speed applications. And already we're seeing the first incarnation of commercial chips. On the bottom right is an integrated circuit developed by IBM over 5 years ago. It was the world's first silicon 60 gigahertz multi-gigabit per second radio. It was a prototype. It had an on-chip antenna that was actually built out of a cavity with a special semiconductor process. But they've perfected this to the point where you're now seeing devices being fabricated for 60 gigahertz radios, replacing HDMI cables and cabling in TVs and monitors in wireless applications in the home. But what we're interested in is looking at how are we going to support the bandwidths for these exciting applications in cellular, not just in the home, but when we're on the move and in urban environments. So I wanted to just show you two exciting results that we've seen and have not yet been published. These are the first public presentations, and they'll be presented later at conferences at the Global Communications Conference. But some new results that show that the cellular of the future will indeed be able to support multi-gigabit per second data rates, which will give us the ability to have on a Qualcomm cell phone, a small cell phone, these great applications of video and high data rate. And one other thing, today, to get to these very, very high, I call them massively broadband bandwidths in handheld devices for millimeter wave radios, the semiconductors are created where digital tuning is done on the analog components. When you build a system on a chip, the digital gates, the transistors, are extremely small. It's the analog components, the RF, the inductors, the matching feed lines that are orders of magnitude larger, so they take up a lot of the real estate. So you can tune these devices with digital transistors to make the analog work in production high quantities. But the antenna becomes the difficult part, because when you get up to these frequencies of 60 gigahertz, 100 gigahertz and above, the coupling loss and the connections to connect a radio transmitter to an antenna becomes extremely difficult. And tiny variations in the packaging around a semiconductor chip, or even the fabrication of the semiconductor itself at these frequencies, are extremely difficult, which is why I believe you're going to see on-chip antennas actually embedded with the RF electronics on the same chip, so that in a simple front-end semiconductor process, you'll be able to create complete radios on a chip, including the antenna. There are myriad research problems with that, but there's promising early research that shows this will happen. And one of the ways to tune analog components today with digital control, I believe, will adapt to tune antennas in fabrication the same way, using the concepts of metamaterials. We actually take advantage of some gross knowledge of the substrate of the semiconductor, the antenna itself, and then are able to tune digitally by inserting or lengthening or shortening electrically the antenna components to make on-chip antennas work. Now, thanks to the work at Bell Labs and Alcatel-Lucent and others, I believe this is a look at the office of the future, and this could be the building of the future, it could be the home of the future, where we take advantage of these massive bandwidths being provided by the optical core, and then look at how things transform in and around the office or the home. We have hard drives today, magnetic media in laptops, but once you get above 5 to 10 gigabits per second, it turns out the cost to transmit data over short distances is actually much shorter using wireless. So you're going to see wireless connectivity between the hard drive to the monitor and to the CPU, rather than magnetic or even electronic drives. In fact, the cost of sending 10 gigabits per second over a copper wire, even as small as a tiny bond wire used in semiconductor fab, becomes very expensive because you have to equalize that high data rate transfer in the electronics. And if you use wireless, you can actually exploit spatial antennas and the proximity to collect the energy. So you're going to start to see wireless replace, for example, the hard drive in the computer. The books on your bookshelf could either be delivered by the cloud, but more likely it'll be stored locally. Books we have may be wireless RFID post-it notes with massive download data rates of tens of gigabits per second in our vehicles. We'll be carrying media around with us either from the cloud or bringing it down locally, and we'll actually have them on small credit card type devices. So the key is, if we can get the backbone with these kinds of data rates, the edge is always going to pull. And we've seen that. We've seen that the fiber optic constraints are being pulled by the applications at the edge, like we saw in the first session. The good news is we're going to be able to get to 10 to 50 gigabits per second wireless links if we open up these new spectrum bands and some of the things I'll show now. So the first thing to understand the data rates that you can carry over a wireless system and how antennas can work to exploit the channel is you have to make measurements. And so we've been making a tremendous amount of measurements, some of the first in the world, at these high frequencies, and looking at adaptive antennas, steerable antennas, to understand the channel and how good the channel is and what kind of link you can have and what kind of multipath problems you have. And what we find is pretty remarkable. When you look at the angle of arrival with different beam widths, it turns out the channel looks very different if you use an omnidirectional antenna versus a very narrow antenna. That's probably not surprising. But the difference between 38 gigahertz and 60 gigahertz is quite different. So we've been making peer-to-peer measurements, which is how a lot of cellular traffic and this office of the future will work, and vehicle-to-vehicle communications will work. We're in close distance and not using large base stations, and also looking at base station applications, fifth-generation cellular with rooftop systems. And so here's the University of Texas campuses, and this is one example of the many measurements the students have been doing during the hot summer in Austin, Texas, and they work very hard. But we have directional horn antennas. We move them all around different locations on campus with different transmitter locations, various antenna heights, and we try to find where we can make a path at these millimeter wave frequencies. What's the signal strength? Where does the energy come from? And what's the quality of the link? And here are a couple of students, Yijun Xiao and Escher Ben-Dor, with one of our carts on the measurement systems. And I got to thinking, the students take this out every day and wheel it all around campus. And what we have on that are racks of equipment with one of the world's fastest channel sounders. It's a 750 megachip per second pseudo-noise channel sounder, 600 times the speed of the original CDMA pseudo-noise sequence developed here in San Diego. And what we found is you can't get higher than 750 megabit per second sounding data using off-the-shelf chips, Echologic. We have to now start building our own integrated circuits to get up to many gigabits per second. So to be able to do research at the bandwidths that wireless is going to need, universities have to get into the chip designing business and create the capabilities to build the same order of magnitude devices that companies will be building in the future. So we're actually doing it at the lab. And you can see, while some students are on the ground, there's James up with the rotatable horn antenna on top of the building, and we're looking at down tilt and angle of arrival and collecting some very exciting measurements. And here's one of the results, very early results. What it shows is, remarkably, at 38 gigahertz, we're able to make a link. That is, using directional antennas at both the transmitter and receiver, we're able to get about 8 to 12 unique paths in which you can carry multi-gigabit per second data at random locations on a campus over distances out to 1 kilometer. This is using relatively low power, less than 1 watt transmitter power. What this means is that 5th generation cellular, the ability to carry data at these millimeter wave frequencies, will work in non-line of sight conditions. It's been a myth that you can't do this in non-line of sight because of huge diffraction. And while that's true on the fundamental physics, we're looking at random locations of transmitters and receivers, and what we're seeing is that you can get a number of links at different antenna angles. In fact, sometimes you can get up to 40 links at 40 different locations, line of sight, of course, if you have it, but if you're not line of sight, there are usually 8 to 12 individual links with 10 degree beam width antennas at the transmitter and receiver, which gives us a lot of hope to being able to exploit these future millimeter wave frequencies. But then when you go on the ground, peer-to-peer, what you see is you have fewer links. That is, if you're not up top with a base station, it makes sense. You're going to have fewer links. There's more shadowing and obstruction. But still, you can get 5 to 8 locations and 8 to 12 at 38 gigahertz. This shows the propagation properties of 60 gigahertz indeed are more attenuative, but you still get 5 to 8 possible links with directional antennas. So that's exciting, and we're continuing that work. But one of my graduate students, James Murdoch, came from the power industry. I was able to get him back to graduate school after he worked in the power industry, and he'd studied how subsystems worked. And we noticed that there are all these papers on green radio, and there's a big emphasis on power consumption and how to build efficient radios. So we started looking through the literature, and there's not an easy way to analyze the power consumption of a transmitter chip or a receiver chip, or how much power do you put in software versus hardware. And so we've come up with a really remarkable result. I'm very excited about this. It's a new theory we call the consumption factor, which allows in a very easy and elegant way to determine the power consumption and to compare different architectures, transmitter and receiver architectures, and to actually compare different chips that companies will build. Because there's never been a very scientific way to understand how to compare power consumption. And the key is this. You break any device, whether it's an amplifier or a mixer or a CPU, you break it into 3 components. The power that's transmitted from that device up the chain through the link, the power that's not used, that's wasted in that device, and then the power that's used by ancillary devices. In other words, in a transmitter, you have a baseband, you have a mixer, you have a local oscillator, an amplifier, and an antenna. The CPU is something that isn't producing, it's not in the chain of the signal path, while the amplifier and the mixer are. The local oscillator is not in the chain of the signal path, so it's an ancillary device. What you do is you study the power consumed by all of those devices, and we call the devices that are not in the signal path, you consider their power consumption. You then consider the signal path devices. And by breaking it down, you see that these devices can be related to their gains of the previous stage and their efficiencies. It's very much like Free's original development of noise figure. Noise figure is a very important communications methodology. We've extended that to power, where you can now understand the power requirements. And we've defined the consumption factor as the maximum data rate you can carry over the consumed power, or the minimized consumed power. We're going to be presenting this for the first time at GlobeCom, but basically you see Shannon's law, the maximum possible data rate on the top, and then the denominator you see the non-path power and the in-path power components. And what's really neat is at the end of the analysis, you get a result that shows that the consumption factor, which is a measure of data rate to power consumed, improves linearly with bandwidth, where you put most of the power in the non-path components. In other words, when you put most of the power in the CPU, in the computing engine, and the RF and the RF chain goes to 0, or if you can make the antenna better, more efficient, if you put most of the power in computing power, you actually get improved usage, much better data to power. Now, people have observed this empirically, but there's never been a theory to define it and to compare the different approaches. So that's a glimpse into the hope of the future. The good news is B goes up, efficiency goes up, which means we're going to keep taking wireless to higher and higher bandwidths. Thanks a lot.
I'm back. Let's see. First of all, some of you in this room probably remember when 1,200 bits per second seemed like it was enough bandwidth because you couldn't read any faster than that. For a while, I was. So that tells you something about our appetite for capacity. Now, you have to understand before I get into this very brief presentation that I'm just a software guy. So I don't know anything about power management at all from the standpoint of the hardware. So I'm actually delighted to know that Ted's got a theory that will help us understand, first of all, how power gets consumed, and second, that if it's the CPU that makes things better, then the software is going to be responsible for improving our ability to generate high-speed radio-based systems. So let me go to the first point here. These are kind of tactics that I think of when you're worried about using up power. I'm particularly concerned when we're dealing with mobile devices that have to use batteries, or perhaps spatial-based space devices that have power that's limited by, for example, solar arrays. So one thing that you want to do is not power pieces of the equipment unless it's necessary to do so. So selectively powering and depowering components on a chipset could turn out to be helpful. Now remember, again, I want to re-emphasize that I'm just a software guy, so if this is stupid, it's okay. I won't be embarrassed when the real engineers come and tell me it's dumb. But I would like you to say something if I've gotten it wrong. Another thing which has fascinated me, of course, is memory technology that doesn't require continuous power or refreshing. The static RAMs and the flash memory and these devices that are, I think, still rather in the laboratories, memristors that have the ability not only to maintain state without power, but also to process things right there in the memory. So you get this very strong integration of both processing and memory, which has the advantage of not having to move things from one part of the system to another. At Google, we're very conscious of the need to compute efficiently, and so when we build our warehouse-based systems, we actually build our own motherboards, and we exclude from those boards pieces of equipment you would normally find in a laptop these days. For example, high-speed graphics chips or rendering devices and things like that, which are not germane to most of the kinds of computations that we do in the warehousing system. And as a result, we get much better efficiency because we simply don't include any of those components on the circuit boards. Another thing that we've chosen to do, and I think even pioneered, is to find ways of keeping warehouse-based systems cool without necessarily having to use excessively chilled water. I mean, we still use water-based cooling systems, but the inlet temperature that we're able to work with is rather higher than most others, and that, of course, reduces some of our power requirements. Qualcomm, if I may be wrong about, Erwin, I may be wrong about the pioneering of this tactic, but I learned it first from engineers at Qualcomm, and that's the ability to decide how much power to radiate based on who you think you're talking to or who can hear you. And the idea of not radiating unnecessarily, power unnecessarily and causing interference unnecessarily, I thought was rather clever, but it led directly into protocols and measurement that helped you make sense of the environment that you're in, changed power levels for transmitting. And ultimately, I think we need to be able to build software that is more aware of the state of the transceivers and the available battery power. There are times when you could transmit, but you shouldn't because you don't have enough battery power and you don't want to exhaust it at a crucial moment when you're trying to remember what you're doing. So having more ability to learn about the state of the system so that the software can change its protocols and tactics in real time is another valuable possibility. Now, I wanted to relate this power question to parts of an interplanetary internet effort that I've been engaged in since 1998 with the Jet Propulsion Lab and other parts of NASA. Here again, we get into some interesting power trade-offs. When the rovers were landed on Mars in January of I guess it was 2004, they were intended to transmit data back to Earth directly to the Deep Space Network. This was the network that was built initially in 1964 with 70-meter dishes in Canberra, Australia, Goldstone, California, and Madrid, Spain. The plan was to transmit data from the surface of Mars at about 28.5 kilobits per second. And the radios that were designed to do that, when they were activated after the rovers landed, overheated. And there was great concern that this would either, continuous use would damage the radios and possibly also components that were in the neighborhood, which meant the duty cycle had to come down. And you can imagine the scientific response to this. 28 kilobits was already wimpy enough, but now the duty cycle went down. So it was observed that there were orbiting satellites that had been used to map the surface of Mars to decide where the rovers were going to go. So the X-band radio that was available could not reach all the way to Earth, but it could reach up to the satellites that were a lot closer. So the engineers reprogrammed the rovers to take the data that they were gathering, and instead of trying to wait until the orientation of Mars was at the right point where you could start transmitting back to Earth, instead they reprogrammed the rovers to transmit data up to the satellites that were in orbit. Now, of course, they're not in synchronous orbit, so they're coming around episodically. They would transmit data up at 128 kilobits per second because there was enough power to go that distance at the higher speed. And because the orbiters were out of the atmosphere of Mars and actually had larger solar arrays, they were able to transmit data back to the Deep Space Network at 128 kilobits a second. So in the end, the way this system has delivered most of the data is that you transmit data up into the orbiting satellites, hold onto the data until they get to the right place in their orbit. Then you transmit the data back to Earth. That's a store and forward network. Well, that's how packet switching works. That's how the internet works. And it was a great demonstration for the scientists that networking in space is more than a point-to-point radio link. It's something I keep repeating over and over. The next example that took advantage of this situation was the Phoenix lander that landed in May of 2008. It was at the polar part, the North Pole of Mars, and there was no configuration of Mars and that spacecraft that could ever transmit directly back to Earth. So they had to use the store and forward technique in order to take advantage of relay to get back to Earth. So those are little examples of taking advantage of store and forward to use power more effectively than you could otherwise. So the result of this effort in the interplanetary system was to develop a new set of protocols in order to overcome things like speed of light delay, which is substantial. Between Earth and Mars, it takes between 3.5 and 20 minutes for a one-way propagation. And the other problem, of course, is that because of the celestial motion and planetary rotation and everything else, you never have a continuous link between Earth and Mars. So you have to hold on to data, just like those orbiters did, until you have an opportunity to transmit. So we literally use the network to store information until it's appropriate to transmit when a link becomes available. And here's another example of the way in which power management is important. You don't want to be transmitting until you know there's somebody who will listen. And so the system, because it's using orbital mechanics, can predict when, in theory, the other guy should be available to transmit. Now, I have to admit to you, when I think about this in a little brain model in my head, I think this is really weird, especially let's imagine Earth and Mars are 20 minutes apart. And instead of transmitting a radio signal, imagine that you have a baseball that you're going to throw to somebody. You have to throw the baseball way before you could even see the guy, forgetting about speed of light, delay for even seeing anything. So you have to throw the baseball at the right time so that he comes around just in time to catch it. Otherwise, he'll miss it. The same problem arises with the radio signal. You have to transmit before he's going to be there because it's going to take a while. This is just not the normal thinking when you are in a terrestrial environment and the delays are measured in milliseconds. So ping, for example, which is a great way of finding out whether are you there here on the terrestrial internet, doesn't work very well when you won't get an answer for 40 minutes. So, round trip times become a real problem. This notion of thinking about and planning for when you should and shouldn't transmit, conserve power until you absolutely have to, don't transmit if you don't have enough power to stay alive, all these kinds of things are very important for making these systems work well. And just to show you that we've actually made this stuff work as opposed to just writing papers about it, we took the ideas to DARPA in 2009 and we said, well, we've got this delay and disruption tolerant networking system, and we hang on to data in the network, and we think you might have the same problem in a tactical environment where you have jamming, radio shadow, ballistic anti-jam, you radiate, somebody sends a missile at you. So we suggested that they should try using something besides TCP/IP in order to make their tactical systems work better. And in classic DARPA fashion, they said, okay, prove it. And they handed JPL and MITRE some funding, and we went off with the Marine Corps and managed to get 3 to 5 times more data through the system using our delay and disruption tolerant protocols than TCP, which we ran in parallel. Why was that? Well, in the TCP case, you have to have a continuous path for real-time handshaking for the protocols in order to get data delivered. And in that system, if there is no next path, the packets get thrown away. In the disruption-tolerant networking, taking advantage of the cheapness of memory, you hang on to the data if there isn't a path to go, and then when there is one, you send it. So we got more data through the system because of that tolerance. We then tested this with our friends in the European Union who funded a project to go and put the delay and disruption tolerant protocols in operation on all-terrain vehicles in the northern part of Sweden. So we worked with the reindeer herders, the Sami, who live way up 65 degrees north in Lapland. We put Wi-Fi services in the villages, and we had the delay and disruption tolerant protocols running in laptops on the all-terrain vehicles. And basically, you wander into a village, you dump whatever data you have, you pick up whatever data there is, and you wander off to another village and you do the same thing. It's like having a data mule that's carrying little side packs around, and the data just moves. And it worked. It was really quite stunning. So then we thought, okay, well, this is supposed to be for space communication, so we ought to really do it for real. We got permission from NASA to upload the interplanetary protocols into a spacecraft called Deep Impact. Now, it had visited the Tetley 2 comet and launched a probe into the middle of it, which blew up in the middle so they could sense the interior materials. So that spacecraft is in eccentric orbit around the sun. It was on its way back towards Earth. And at about 81 light seconds away, we uploaded our protocols and we ran a series of tests for about a month, communicating back and forth at fairly significant distances. I have to tell you that it's more fun than anything to have an ordinary conversation with someone when the term 81 light seconds comes up. Because, it just, this doesn't normally show up in day-to-day conversation. We've also uploaded the same protocols to the space station. We have several devices up there that are running the interplanetary protocols. So the whole idea here is to take advantage of knowledge about the condition of the systems that you're operating in order to be attentive to power utilization and choosing when to transmit and how much to transmit and at what power levels in order to conserve things. And that's the challenge for the protocol designers, so that they don't build protocols that require too many transmissions back and forth in order to coordinate everything. And that was what drove us to move away from the TCP protocols to a new set that are much more conservative about how much they have to transmit and how much handshaking has to go on. So I'll stop there so we can reassemble the panel and have a further discussion with everybody here. Thanks very much.
So there'll be two different panel discussions. The first one will address the 4 presentations that you heard now, and then I don't know how Dave intends to do it. He's going to call up the G-Whiz guys to join the realists up here, and I don't know, maybe they're going to sit on these guys' laps or something, but I'm not going to worry about that. Dave can worry about that. So I'm opening the floor to questions and discussions and comments for these 4 very interesting talks that we heard.
Mr. Chairman, are you not going to allow the panelists to debate with each other a little bit?
Oh, absolutely. That's when there's a
okay,
lull
all
in the
right.
questioning.
Well, okay. Well, I was going to ask Ted about FreckleNet.
Okay, so the floor is yours.
Actually, I do have a question. If you start using spatial techniques in order to get higher bandwidths, the first thing that comes to mind, especially very high speeds, is whether or not differential delay is going to make for a really tough resynchronization problem. So I guess that's the first question I have is, how bad a problem is it to transmit over those multiple carriers, assuming that you're trying to propagate bits at the same time?
Right. Yeah, we call that multipath delay spread in propagation. It's the time delay, the echo effect. And this is interesting because it turns out that's not a problem at all. As we get wider and wider bandwidth, and really Qualcomm pioneered this concept, as you get wider and wider in bandwidth, you get greater frequency diversity, which makes the issue of fading and equalization, you can do equalization different ways. But that said, it is an issue undoing the delay to resolve the bits. This is where radio architectures are going to change fundamentally. Right now, when we do equalization, oftentimes we do it digitally in our DSPs and our special multi-cores. However, when you get to such great bandwidth, that's going to become analog. And you're going to start seeing new kinds of equalizers that are implemented in analog, just the way we're having to do it on 10 gigabit Ethernet. So we went to digital, and digital is going to become analog again
so
to get the huge digital data rates. Yeah.
Thank you.
So perhaps we can stay on that same topic, because differential delay will also rear its ugly head in the multi-mode and multi-core propagation thing. And so maybe Peter or Bob would like to describe the problem and how people intend to try to solve it over thousands of kilometers rather than over tens of kilometers.
I mean, the differential delay, of course, is a huge problem if you talk about MIMO for optical, because you can have many thousand bits delays over 1,500 kilometers, and then you need to bring that all back with an adaptive equalizer that's really whatever 50 by 50 matrix if you want, and that fitting that into an ASIC at 100 gigabit per one of these 50 by 50 channels is a real challenge. I mean, the best we can do today is, actually I have one of these ASICs here. That's a 100 gigabit commercial product. That's the ASIC that does essentially 2 by 2 MIMO, not for spatial multiplexing, but for polarization multiplexing, which is a very similar thing. But that's the best we can do today, 2 by 2. Now we have to scale that, and the differential delay that this can handle is by far less. It's on the order of maybe 10 bits or so, but not, or 10 symbols, but not 100 or 1,000 symbols. So we need to come up with techniques to simplify the DSP and also improve the physical layer to get the differential delay down.
But it makes you think about fiber networks in a completely different way. It used to be when you're installing a network, you just want to make the cores line up and get the best splice possible. But now if you have multi-core fibers, for example, there's different delays for the outside cores than, say, for the inside cores, just due to bending and propagation constant changes. There might be an issue of how you splice multi-core fibers to multi-core fibers, whether you want core interchange. How often do you have to do that so that the center core is not always the center core and the outside cores? So it's like Peter said on his last slide. I mean, the number of problems, it's just like fiber optics being reinvented all over again. So it's a really exciting time. Okay, now I guess we'll let the audience finally participate. Vint, you got anything more to say? Nobody's asking questions.
I've got something to say.
Okay.
As
I
the
have
wireless,
a question too.
but
So go ahead,
as the
Frank.
wireless guy on this panel, I just want to say for 30 years we've been hearing how memory sizes are increasing by a factor of 1 million. Clock speeds have increased by tens of thousands. All these things have been increasing. Finally, the carrier frequency is going to increase.
At last. So I have now looking at this from the programming point of view, I'm imagining I'm a router and I'm connected to one of your FreckleNet things, and stuff is arriving at an incredible rate. So my first question is, what is this going to look like to my software? Am I going to see packets coming in on one core? Am I going to bind a particular communication virtual channel to one core, or am I going to get bits coming on all cores that have to be reassembled? If I have a multi-core processor, which I hope we have, how do I multiplex the packets to the different cores, not the optical cores, but the computing cores, so that I can use parallelism in order to process the packets at the right rate? How do I do the multiplexing, the demultiplexing? Has anybody thought about that?
Yeah, that you're asking, how do we drink all this data? I mean,
Yeah, without having it all turn into Kool-Aid.
Right.
Yeah, that's right.
well, that's the applications that we saw in the morning session. I was thinking the same thing. How do you collect all that data and deal with it? There's a lot of work going on in parallel memory, parallel A to D, new ways to do storage. But that's a good question, which I don't know the answer to. How are we going to be able to handle multi-gigabit per second data? It's easy when you have an application such as all 82 TV channels, 70 which you never watch, all coming on the same channel, for cordless replacement. That I get. And it's easy to understand in a network, in an enterprise network where you'd have that much data. But that would be a great question for the morning session. How are these applications, for example, in the cell phone of the future, going to be used?
But we're supposed to be the realists to figure out how to do that.
Yeah.
They're the ones that get to dream about this cool stuff. We're supposed to figure out how the hell you actually make that happen.
Well, there's going to be a lot of parallels.
Well, yeah, but we can have to have fixed length packets or something so that there's TDM kinds of tricks you can play that I can listen now because that's the next packet, or do I have to have variable length packets? How do I know when one starts and stops? You know the answer. Anybody else going to help? Bob? No? Anybody in the audience got some ideas? Bob Lucky? You're usually good at this stuff. Nope, not a thing.
Erwin's got something to say to this.
Erwin?
Well, even now with the much lower data rates than you're talking about there, but still high data rates, with multi-carrier approaches, one has that same multiplexing issue. You break the incoming bit stream into several streams, send it out over several carriers, and then reassemble at the other end. And so that kind of game is already being played. There was also the interesting issue with multi-core processors and this issue of how much energy you're using up. And one of the things we've been very careful about is when we put multi-core on a chip, we also allow them to be clocked differently or put in different power states, because you're not going to be able to provide equal loads on each one, and you don't want to waste the energy. And so far, many companies haven't been paying attention to that, but I think that needs to be done as well.
So if I could just follow that up a little bit, Erwin, one of the things that it appears to me to be a problem is that the multi-core chips have enormous processing capacity. If we could just get the data to them, and I think we're starting to run into the problem of moving data on and off the multi-core chip. So it feels to me, very naively, that we're hearing about super high-speed ability to transmit information, probably faster than you can read it or write it onto a local disk. The net is faster than your disk drive. But getting off of the high bandwidth transmission system and into the high capacity computing core now sounds like it could be an issue.
Yeah, well, there have been tremendous advances in memory, fast dynamic memory. It's remarkable. That's scaling with Moore's law. So getting the data and getting it in a static location is not a problem. The problem is, then what do you do with it when you have the data? That's what I'm thinking, and that's where I think the applications piece has to be part of that. John has a comment.
Okay, we're getting a transmitter for you. Hang on. He's right here.
I have a question for Peter. Peter, in wireless MIMO, we have the benefit of getting multipath to provide diversity effects. Do you have any kind of similar effect in fiber optic MIMO? Because it seems to me that if you don't have the diversity of benefits, you pay a very large penalty in the interference that's encountered.
I think this is exactly one of the topics I discussed with Jerry Foschini so many times, and it reflects the clash between the different boundary conditions. We have totally different boundary conditions that make the thinking different, and the diversity concept actually never comes up. Because what we have not a constant transmit power, we have a fixed transmit power per mode. Then we are able to launch all the channels to detect all the channels. It's a complete orthonormal set. So in the ideal case, our channel matrix is just a unitary. And in that sense, the diversity it doesn't really come into play. I don't know if I answer that correctly, but. Oh, no, but if you have a unitary matrix, then you can totally invert it and undo it without any impact on capacity. And that's that's the zeroth order model of a spatially multiplexed MIMO transmission. You excite all the modes, everything. You don't have modes that leak out. Like in wireless, the receive antenna never collects the full information. You would have to have a hemisphere as a receive antenna. Think of it like that. If in wireless, the equivalent model is you are sitting here and the base station is a hemisphere around you that collects all the spatial modes that you are transmitting. That's an equivalent of the optical model. And then you can think of a unitary transformation then that transforms the modes that you send into the modes that you receive, but you still receive the full information. So now problems occur when the matrix is no longer uniform because of the differential modal loss or differential modal gain. That's when outage and stuff comes in.
I see. So this transformation is lossless, basically.
In the zeroth order is lossless, and that's what we'll be striving to do. And then once you build your amplifiers, you build your connectors, you build your splices, they will have some differential modal gain or differential modal loss. And you need to keep that to within certain bounds in order to preserve quasi-unitarity of the matrix.
There are two comments that were made at two different contexts, and I want to put them together. Ted made a comment about gigabit interfaces inside the computer systems, memory talking to the CPU or the storage talking to the CPU. And Wendt made an interesting comment that networks are much faster than, let's say, disk drives and storage systems. And it makes sense. If the network speeds are high, you would rather put a networking interface even talk to your hard drive. In fact, that's what you do when you take a hard drive and put it on EBS, for example. The thing that I'm wondering about is, even as these interfaces evolve, are we getting ahead of what is possible in the software stacks, which are already so deep? They're not very error tolerant. When you talk to the memory, so when a processor talks to a memory versus a transmitter talks to a receiver, the likelihood of failure is not assumed. And we can go over where this is handled. But our software stacks are incredibly fragile. And you could open up the computer system and perhaps put a serialized interface with very high speed. So my question was, are we getting ahead of what is actually possible from a total stack point of view or total systems point of view?
You're the software guy.
Yeah. So the answer is probably yes, that you could pull this off. I'm not going to sit here and try to design it on the spot, though. Could we take this up as a side conversation after we're done?
Richard?
Informative to me, not judging quality, but information content. And you mentioned, Peter, you mentioned various degrees of freedom that you had, time, space, et cetera, et cetera. You had 5 or 6 of them. But you did use the continuous Shannon capacity to judge against it. What about going down to a Poisson model? To what extent? I was trying to find other degrees of freedom that you hadn't used. looking at individual photons in a Poisson model, what is the capacity then, and is there something to be gained?
That's an excellent question. And in fact, there is a information theory for quantum states that's been first formulated by Jim Gordon and then extended by Holivo. And there is an expression for the, similar to Shannon expression for the channel capacity if you include all possible quantum states that you can have. And that does not only include single photon counting, but also it includes entanglement and all these advanced number states, all quantum states that you can have. But it turns out that the capacity that you get at good spectral efficiency is not that much higher than in the classical regime. You can, at very poor spectral efficiency, you can get significantly higher, at very, wait a second. You can get much higher spectral efficiencies at very poor photon efficiency. If you sacrifice the sensitivity a lot, you can get very good spectral efficiencies, like PPM, for example. Pulse position modulation, when you go to a lot of slots and do photon counting, you can increase the spectral efficiency a lot at the expense. You increase. It's always you increase the sensitivity at the expense of spectral efficiency. But in a reasonable regime of spectral efficiency, you get about the same sensitivity with quantum than you got with classical.
So let me ask about a different aspect of radio. One of the things that we've not done at all in the protocol and software world is really seriously take advantage of broadcast. You know, we turn broadcast channels into point-to-point channels with Wi-Fi, basically. What would happen if we started writing protocols that took advantage of knowing that when you transmit something that multiple receivers might hear it, and therefore you don't have to send to them individually, or when you transmit something and the guy that you're hoping is going to forward it doesn't get it, but somebody else does and knows how to do that, can we get more than the classic point-to-point Shannon capacity by taking advantage of broadcast?
Yeah, that's happening. That's actually in development and part of the future standards with a number of techniques, cooperative transmitters. Sergio had a comment on that, did you?
Yeah, you want a microphone. It's coming. There we go.
Yeah, there is, in fact, the technology of fountain coding, which...
yes, I'm familiar with that, right?
Yeah, so it's exactly what you're saying. So instead of sending the same information through different channels repeatedly, what this technology does is that some channels may be much better than others. And the advantage is that instead of catering to the lowest common denominator, then the users that see a better channel can switch off faster than the users that see a bad channel with a lot of erasures. So they have to wait more to get all their data, but at the end of the day, the fountain code enables you to do that at pretty much close to the Shannon capacity.
That's cool.
For
Thank
channel.
There was a question over here.
Thank you. I'm Mark Gornberg. My question's for Ted and perhaps for the panel. And first of all, Ted, I wanted to thank you for sharing your work at the 3860 gigahertz level with us. It's very exciting to see that. My question is, going back to your very first slide on the whole spectrum map, given the differences in distances, interference, the size of these bands, do you have any recommendations of what we should be doing about spectrum in this area? And is it different than we've done in the past? Is this a sea change?
I think it's a sea change because to develop these new semiconductor capabilities, which are going to be very challenging on the RF side, above 100 gigahertz, and a whole new way of using antennas and space as part of the future of wireless. I think that federal regulators should look at opening very, very large swaths of bandwidths. And I think if you look at where you have high attenuation and low attenuation, those are natural segments to provide unlicensed playgrounds, if you will, that allow the future generations of wireless devices. and with meaningful spectrum allocations. You know, a 3% bandwidth is narrow band. You go to 200 gigahertz, 3%, 6 gigahertz. You do a 5 or 10% allocation, you're talking 10, 20 gigahertz of bandwidth. Those are the kind of bold moves I hope the FCC will do to inspire new development and new products, you know, which will be available in a decade or 15 years from now.
Could I just reinforce that? I've been looking at public safety networks recently at the request of Anish Chopra, the CTO. And one of the things I am excited about, especially after hearing the presentations today, is the possibility of building a national scale public safety network that operates in the 60 gigahertz and up range. First of all, we get reuse of frequency on a nice basis because of the attenuation. And second, I can build mesh networks now operating at incredibly high speeds, pumping, you know, video, data, and every other kind of audio as well, all in the same capacity. And having a wideband channel to do that in gives so much opportunity for development and experimentation, and might even have a good GDP effect. If you look at what happened with Wi-Fi, people invented all kinds of products and services because they didn't have to get licensed spectrum to do it. And at these higher frequencies, the reuse, B, the speed, you know, capacity, and the opportunity to try things out, I think is dramatically important.
So you still have time to tell President Obama about this, his speeches tonight, this improvement in GDP.
Yeah, let me get my mobile here. You have a hand up here.
So on the same topic.
There's a microphone coming.
On the same topic, I'm tempted, in your tradition, to give a name to it and call it sci-fi.
Oh, that's so bad.
But
-2.
But when do you think it would be commercially viable, mainly from a cost point of view?
Well, my honest belief is that all of these things have tended historically to get less and less expensive, especially as you get experience building chipsets, experience programming them, and experience with economies of scale. So I'm clearly making a presumption that at some point these things will be economically attractive. I'm certainly not proposing that we outfit every fireman with a $10,000 radio. I know that's not economically sound. But the ability to do all modes of communication using a single broadband system, from my point of view, is extremely attractive.
And I think there are two things that have to happen kind of from both ends. One is you have the infrastructure, the core of the network that you're working on and getting up to terabits per second there. And then there's at the chip level, the semiconductor level. And the advances there, you know, getting down to 20 nanometer transistor gates and processes that are continuing to be developed, and Moore's Law continues to push. You're starting to have today commercially fabbed devices with transit frequencies up to 500 gigahertz. You can make them pretty cheaply. So pushing that up to 1,000 gigahertz and above that's going to happen. It'll happen faster if there's a spectrum allocation or an opportunity to build products. And you know, that's the role of the FCC, and I think the spectrum allocation. And it feels to me that in this country we've kind of fallen behind. We had a lot of very maverick efforts in the 80s and 90s with the ISM band and the 60 gigahertz band and the effort at LMDS. You know, and we haven't had any big spectrum allocations yet. That's where you basically have the license to go and think big and invest. And you know, hopefully we're going to do that as a country, because I think we need to handle all those applications and those massively broadband capabilities and get them into the hands of our consumers. And I hope the U.S. is first there.
You know, I had follow-up questions here on the MIMO.
Where are you?
From here.
Thank you. Okay.
This was assuming a linear channel. Fiber is not always linear. Any comment on that?
Yeah, you're right. I mean, the M-fold capacity increase that you get for the linear channel, and as I said, nonlinearity will ultimately limit all this. But this is a wide and open field. Nobody knows at this point how MIMO will behave in that type of nonlinear environment, which has memory and nonlinearity, and they are coupled, plus noise that is added all along the way. So you have these three effects that all couple together in a very, very tricky way. So all theoreticians, go ahead.
The nonlinearity is going to be tough, I think.
Yeah, Ted, with some of your narrowband high-frequency antennas, it looked like the COTS had the antennas mounted on tripods or whatever. How much have you done on acquisition and then tracking the movements if a handheld is still slow, but have you been able to deal with that?
Yeah, good question. We've been talking about it, about having automated measurement capabilities to move things and to down tilt and to kind of simulate actual body motion. We haven't done that. But the good news is the Doppler is going to be really marginal, even though the Doppler goes up to 10, 20 kilohertz. When you're talking about data rates of several gigabits per second, the Doppler is such an easy thing to deal with. It's really going to be body loss and change of antenna orientation that's going to lead to a whole new field, and you're starting to see it in some of these 802.11 AD 60 gigahertz standards, where they're looking at antenna pointing algorithms that can adapt very quickly and have that built into the PHY and even the MAC layer, so that you can kind of keep the link and have the antennas steering at both the transmitter and receiver. That's really a wide open area. And we'll need to automate and do much more measurements to be able to understand that, because that's a dimension of wireless that's never exists, the idea of having actual antenna steering as part of the fundamental communication protocol. And also the beam width itself. For example, you don't want an antenna to be very, very broadband in its beam when you have a tough link to make. So you've got to be able to quickly adapt the beam width as well as where it's pointing. And then also you don't want RF energy pointing into your eye. Your eye is much more sensitive than any other part of your body for absorbing RF. So we need ways to quickly detect.
You shouldn't have said that. I mean, that's it.
No. But we have to have smart antenna pointing techniques to make sure that the energy goes to where we want it and quickly adapt. And we're not going to know that till we get more
So you just
advanced.
You introduced another really hard routing problem then, because when you have a topology which is being dynamically adaptive, you have links created that didn't exist before. And so a lot of the routing algorithms assume there's a topology and it comes and goes, but it doesn't create new links, unexpectedly or on the fly exactly. So routing in this much more dynamic topological environment is actually going to be harder than the traditional kinds of tactics. So we have a whole new set of
Well,
problems.
there's a whole new dimension of space.
Yeah, exactly.
In the back there.
How about environmental effects like rain and fog at these frequencies? Do you have a word about that?
Yeah, there are actually a lot of measurements that have been done in the satellite world, and we've done some. Turns out hail is the toughest thing.
Hail?
Hail. You can have 20 dB, 25 dB outages with terrible hailstorms, but actually rain's not terribly bad, nor is fog. 3 to 5 dB, typically below 100 gigahertz. So these will be issues that have to be considered in the design and the deployment of future cellular systems. But it's more of an issue than at the 3 gigahertz and below band.
I'm not a communications guy, but I used to remember there was meteorite communications for terrestrial systems that had a similar kind of challenges, where you had links as an aggregate of meteorite trails forming over millisecond timeframes. Are any adaptations or signal processing from those days applicable to what you're talking about now with antenna locks?
You're talking about meteor scatter, which was a remarkable way of communicating 30, 40 years ago, before satellites.
Yeah.
The thing they used in meteor scatter were really directional antennas and finding the vapor trail and pinging off it. So in a sense, we're kind of doing that, but now instead of antennas that are as big as this table, we're looking at antennas that are smaller than your fingernail and will be embedded in the device. So, and that was a very slow data rate, very bursty channel. You know, we're talking about making very reliable systems. And to answer your first question, you asked about the software stack. The way wireless systems are built today, anything commercial, there's generally a standardization process, which has worked so hard to accommodate all the possible channel conditions, all the possible modes, all the possible ways of using the device, that the layers, the MAC and PHY and the network layers generally have taken out all the errors that get passed up to the software stack. So generally, you don't have to worry about the impedance matching, if you will, of the data coming into above the network layer. That's all. That's a job of the physical layer and network layer folks.
I think that's optimistic, though. That's why the fountain codes and things like that might turn out to be valuable.
Just a comment and then something else. But years ago, I gave a presentation advocating a meteor scatter propagation to the Army as a method of covert communication, because only the person you're trying to get to can get it at that instant. And Edward Teller, the father of the H-bomb, was in the audience, and he stood up and said, "No, this is the way to do this. Is you just put up a satellite and you have a laser link down, and you get data rates, and it's perfectly fine." It was quiet in the room for a while, and then a general stood up and he said, "Dr. Teller," he says, "your idea is fine if we fight the war on a sunny day." Yes, right. He was the father of Star Wars also. He passed away. But, this is neither a comment nor a question, so I don't know what it is really. But I'm kind of fascinated with the proposition that the data traffic is continually growing exponentially at a given rate. And I think it's one of those laws of nature, and the composition of that traffic changes, but the total continues to go up. And at any given time, it's going to be different things. I mean, the number of users on the internet is probably tapering off to some degree because we're going to saturate the whole world. But data rates are going up. And then recently, YouTube has been the real culprit. Now, I've got my granddaughter in the 3rd grade has been uploading these videos of her dog, to YouTube. I think nobody's ever going to watch this stuff, but it's out there. So I had this great idea how to get a lot of efficiency out of the network. It's when she uploads one of these videos that the network rejects it and it says it's been rejected because it's useless. But the mystery of all this is who is using all this stuff. And I got this email recently from Google. Vin, you probably sent this out personally, to Google Analytics, and it said they made general observation about the traffic on websites, and they say it's down this year, actually. And it's very interesting, the traffic per website, is down. Obviously, the number of websites is going up at some rate, the number of users is going up at some rate. The whole thing is really fascinating, but when you put it all together, and you get this curve that overall history is going to go up, and I believe it will continue to go up at this exponential rate. But what it is and what it's composed of, human traffic and machine traffic and all that, will vary greatly at any given time. Maybe we'll saturate YouTube in a while. I don't know. But so, as I say, neither a comment nor a question, but a mystery.
But we at Bell Labs actually have a different explanation when we're challenged, when we announce the latest, greatest capacity record, and somebody says, who the hell needs all this capacity? And we just say, well, right now your kids are stealing music off the internet. In a couple of years, they're going to want to steal high-definition, full-length feature movies, and it's our job to give them the infrastructure to do that.
Bob, I think that the use of capacity is not unlike the answer that was given when they said, why do you climb mountains? Because they're there. The existence of the capacity somehow drives people to want to do something with it. And that's why applications happen when they are technically supportable. I remember trying to do a computation to see how many blogs were there and how many people were reading them on average per blog. And I think I got 1.1, which suggests that the person that wrote the blog read it and his dog read it, and that was it. The other thing I think I'm seeing happening is that people will turn to network resources because it's economic to do so and convenient. So how many of us don't remember stuff anymore because we can look it up or Google it? I mean, I can confess Google is my solution to Alzheimer's. I mean, I can't remember people's names, and I ultimately end up either looking at my email to see if I got an email from the person I can't remember, or I look something else up on one of the search engines. So I think this is part of the driver.
And I think it's also the transformation of media, the actual way media is going to be delivered and kept. You know, we have books on our bookshelves. And if you converted all the book titles into electronic data and sent it over the internet, that'll take some bandwidth. I think, you know, the fact that Amazon's now shipping more
online soft books than
hard books. I mean, that's a lot of data. So I think more and more our society is going to move towards electronic content, and we'll be using that data, and I think that's part of the driver.
Actually, there is a corollary to what you just said. If you think about the media that we have today, music, video, printed material, and things like that, but there's also objects, digital objects, that are not interpretable or presentable or renderable any other way than with a computing device. You know, a spreadsheet, for example, or a presentation that isn't just simply printable because it has interactive features. At some point, as our appetite for using these complex objects grows, we will have no other way than to move them around and store them and use them than to go through the net and through these computing-based devices. And I think that is forcing a substantial amount of traffic on the net, is simply these complex objects that have no other way of being rendered.
I think Bob's question or comment or whatever it was actually about this sort of fundamental growth rate and believing that it's going to go on. And I think the reason that it stays so so smooth is that because we've seen very smooth improvement in semiconductors and so on, and the ability of people to use it is very fluid. If I I'm lost somewhere and I try to use Google Maps, and if I have good bandwidth, I use it, and if I don't have good bandwidth, I don't. I do something else. And as the bandwidth gets better, you just use it more, and it's like air. You don't really notice how it is that, but there's always more that you would do if you had more connectivity. And I think until we run out of that, we're going to see this continue the way it has been.
Actually, the other analogy is like closet space. Who has any empty closet space in their house? And if you built another closet, would you have any empty closet space? No. Question over here.
That actually brings me to my question, which is, are you aware of any research that shows how not having to store these physical objects in the future might offset some of the energy usage that having everything on my cell phone will take up?
I don't know of work on that grand scale, but I think that's a great society question to ask. You know, where are the trade-offs? You know, you can easily look at books and think of the transportation cost and the cost of trees, and but I'm not aware.
Well, actually, I'm not sure that I could cite. Maybe if you go to Google Scholar, this would probably be a useful step. But honestly, there's an obvious trade-off between transportation and communication, whether it's working at home and not commuting and things like that. There has been a persistent worry that computing and communication devices are consuming an increasing fraction of power. And so there's a question about what that trade-off is. I still believe that efficiencies, based on the things that we were hearing, will benefit us as we move away from physically having to move move objects to being able to move their digital analogs, including not having to move our bodies. And anybody who travels a lot today probably would like not to do so for reasons having nothing to do with energy conservation, but just sanity.
So I've been ordered to bring this session to a close, but it's an artificial ending because there's another panel discussion that immediately follows. So if you have further questions, just ask Dave for permission to talk.
So So we get to sit down now.
Good. Yeah, no, please stay there. So will the GWiz guys come up and join our panel?
Oh, this is everybody. Oh, my goodness, me in a handbag. Okay, so let's see. Who do I get to be now? I'll be Andrew for a while.
Okay, I'm David Payne, and I'm the chairman of the Marconi Society, and so it falls to me to wrap up today fascinating talks with the final panel meeting. So our concept when we put this together was based on a number of observations. One was that it was like ships passing in the night with their lights out, that often the various proponents of different technologies and the content providers were not speaking to each other that much. I've been at numerous conferences where the wireless side is completely ignored because I'm an optical guy. I've heard the opposite on the occasional times that I've been to wireless meetings. And moreover, I've had some interesting discussions recently with our computer science people and realized that they had absolutely no idea of what was carrying all this data. And I asked the question, is there something we could do that would make your life different? And vice versa. And we've had a number of people addressing those things, so which was very refreshing for me. In order to make people really think hard, we also pitched this thing as to ask the question, what would the internet look like in 100 years, or indeed would it survive 100 years? Andy, I think it was you didn't like that idea, on the basis that nobody could predict 100 years. But let me say that's precisely the idea behind the title. So we thought, let's run it through some young scholars, because they're less inhibited, don't mind being as wrong as we older guys tend to do. I don't want to end up on my name on some of those predictions, right? So, yesterday evening, we had a panel meeting with the young scholars, which are now called the Paul Barron Young Scholars, in honor of Paul Barron, an early ARPANET pioneer who passed away sadly recently, and a Marconi Fellow. And we asked them to imagine what the internet would look like in 100 years' time. And they concluded universally that, yes, the internet would survive the next 100 years, but they weren't so sure that the human race would. Which I thought was very creative thinking. So let me tell you a little bit more about, as way of introduction for our panel here, what the young scholars concluded when faced with that question. Not surprisingly, since they have driven a lot of the applications we have today, social networking, for example, they felt that the internet would continue to grow for the next 100 years. I haven't done that sum, but imagining the data rates that 40 years of doubling every 2 years will yield is a pretty scary number. But that didn't faze them at all. They were quite happy with the idea that it would continue to grow and there was no signs of saturation. They thought, however, that today's emphasis on social networking would go away and it would become a commodity. It would just become a normal part of your life, not what it is today, which is a novelty. I watch kids doing it all the time. I think they'll get tired of that. So
The young scholars also recognized very much what the panel has today dealt with, which is there are significant problems in front of us on capacity, providing the capacity that will keep the internet growing at that rate, and in particular on power consumption. Not surprisingly, young people are concerned with green issues. On security, one of the things I took away from them was the surprising observation that they were not too worried about it. They did not feel that, as somebody put it, the internet would become a badlands, a wild west where you ventured at your peril and as little as possible in case your credentials got stolen. They felt quite relaxed about that. They also felt surprisingly relaxed about the different form of privacy which the internet today is yielding for us. And it was interesting that I worry about it, which is why I'm never going to have a Twitter account and I don't have a Facebook account. But a very different perspective from the younger people, which is a different form of privacy will emerge based possibly around Google's new innovation, which is smaller social circles, rather than a broadcast to the entire world. So that was an interesting observation. The final thing that I took away from them was very interesting indeed, which is that we now, with IPv6, have enough addresses to cover, somebody said, every single 1 foot on the Earth's surface, and which means that everybody could be assigned an IP address at birth. And the interesting observation about that is you wouldn't have to worry about having a name anymore. You would just refer to yourself as 192.168.0.1. Will that catch on? I'm not so sure. But it's an interesting observation that you're born and assigned an internet address on the day you're born. So that was the results of the Young Scholars Panel. And I wanted to share that because not everybody was there at the Young Scholars Panel with the panel and get them to perhaps make any observations or comments. Do they find themselves aligned, for example, with the conclusions of our young scholars who are the internet engineers of the future and hopefully Marconi Fellows of the future? So does anybody want to take that one?
I think one item you omitted that did catch my attention was the feeling they had that within the next 100 years one would be able to wear a small cap and tap the ideas, the thoughts directly from a person is having. And my first reaction to that is that if you think you've got piracy problems now, that would really blow the whole thing. I mean, how do you... So then you have to figure out how do you encrypt some of those ideas in your head. That's a little harder. Seems to be some feeling here that the traffic on the internet will continue indefinitely to grow at 2 dB per year. And it seems to me that, in fact, will not happen. We run out of people, we run out of videos, we run out of ability to make use of them. So at some point, we're going to see that same saturation that's occurring on various fiber approaches, it seems to me, on the requirements.
Thank you.
Let me just address that one, because I think it's an interesting point. I think it's unassailable what you say, that at some point you run out of things to communicate it. Yet, I think we have all said it for every time we've looked at this for the past 20, 30 years. We said, well, at some point it's going to saturate. And I think probably the saturation would have to come on our ability to do things like on the computers or on the technologies, and then the ideas of how to use the stuff will dry up. But I'm not sure I believe that it would just dry up otherwise.
Not dry up, begin to saturate.
Right, but I mean, those new ideas.
The amount per person and machine begins to hit some reducing limits. I was
trying to think, video again is much of the traffic on the internet today, as has been commented on. And so I thought, well, we can only watch one picture. And then I said, well, some of us have, a few others. But across those few others, you can run at a much lower data rate. So maybe that doesn't really multiply up. So again.
But it's not just the cached video kind of thing. It's the real time that really blows bandwidth. I mean, if you think of Panasonic's LiveWall, for example, which I'm sure many of you know, like a giant TV screen that fills the whole wall of your living room, where you can immerse yourself into the living room of another family. In 100 years, we'll all have that. I'm very sure. And then if the whole population transmits like giant videos, maybe even 3D over all real time. I mean, that's enormous bandwidth.
A quick comment to follow before I posited that the internet will survive as a simulation in the domain of whatever's next, and I would expect that would be a larger thing. Wouldn't you think?
Yeah, rather than asking the question, will the internet survive? I mean, even if it doesn't, something else will come along to perform the functions that it performs now because we found them too valuable not to do. So I'm less worried about whether the internet survives and more interested in, if it doesn't, what will replace it, because we will need something. And whether that's quantum communication or something else, I don't know, because right now the physicists tell me that doesn't work. In terms of the increasing bandwidth, the one thing which might continue to push that curve is that the more devices that we incorporate into this networked environment, including instrumented buildings and cars and instrumented roadways and all these other things, the reporting and control and adaptation functions could conceivably require a substantial amount of interaction. A lot of it will be kind of localized, sort of a Pareto curve thing, but there might be a substantial amount of it. And if we are trying to coordinate, for example, power generation and distribution, especially if the generation becomes very distributed because we're using, green energy generation in each home, things like that, the distribution of functionality could produce a substantial demand for capacity on top of everything else. So it's not just the people that are generating or consuming information. It may very well be a lot of other systems.
Just continuing with the thought about whether or not humanity will survive, beyond just the living form, our idea of what humanity is. If you think about the internet as our communication platform, our information platform nowadays, it's definitely driven us to a more reactionary state. Things, the way in which we act as humans has evolved dramatically in the last 10 years because of the internet. And so the human race as we know it is going to change, that's for sure, because of the fact that we have this, almost like this higher plane connection to anywhere in the world, to any other mind in the world instantaneously. And everybody has an equal voice, everybody has an equal amplitude of voice. So one person who's really thought it out can have the same impact as somebody who hasn't. And I think that's a scary liberty.
Indeed, that's it's a very scary world out there sometimes. I once made the quote that probably deserves living up on our list of quotes, which is that information can only be a force for the good. And it seems that the bad guys have other ideas on that. I wanted to take some questions from the floor.
So one of my questions, you talk about an internet that's capable of holding all this traffic, but the problem is for me, seems to be that you can have a boat that's built to hold 100 people, but if all 100 people get on one side of the boat, it swamps the boat. And I had an experience a year ago when my son, who is at University of Oregon, went to Berkeley. He came down and we went to the Berkeley-Oregon football game. And you get all these techie users with their smartphones, and he sat on one side of the stadium and I sat on the other side, and there were tens of thousands of people there, and we're supposed to find each other afterwards. No problem, we've got phones. Hour and a half, couldn't get a message through, a text message, a phone message, anything. Can you build a system that can hold that traffic?
Sure. Yeah, that's a capacity problem. Plain and simple, cellular carriers face that. More spectrum will help solve that. Lower cost infrastructure will help solve that. Technology will solve that, but you're going to need more spectrum, as we talked about today, to be able to solve the capacity.
Well, if you're talking a stadium, it's not a you just need more cell sites, basically, each with a shorter range and able to communicate with one another. And they usually, someone didn't look ahead at that point, but usually they do bring in cows or movable cell sites to provide that support. There are emergencies that you can't predict, of course, that overwhelm you until finally you can bring the equipment in. But you can get the frequency reuse actually even today to handle that kind of traffic.
So actually, I want to push back only slightly, not on your question, but on what Erwin was saying, on the following grounds. The cell system design involves base stations communicating with clients. And I'm very attracted to mesh types of systems that sort of help each other because, you know, the device not only can be a source and sink, but it can be a relay as well. And so in some instances, the fact that there are more devices there operating at high enough frequencies could wind up helping you build the mesh that carries that communication. So that's an alternative. I do have one observation that nobody's made during the course of yesterday or today about whether the internet will survive. There is a question about whether it will survive the onslaught of questions about internet governance. The question is whether governments are going to let the internet survive, because there's a lot of sensitivity and worry about the power of the internet based on things like you were saying earlier and others, that this is such an incredible tool that it threatens governments that like to prevent their citizens from knowing what's going on or from coordinating. So the biggest concern I have right this minute has nothing to do with technology, and it has to do with somehow managing the process of bringing this system into a rational space so that the harms that it can do, and let's be honest, harms can occur in the internet caused by people who are in different jurisdictions, different countries. We have to figure out how to manage that process so that we don't destroy this network in the course of trying to protect everyone from the potential harms that can occur.
And if anybody wants any evidence of that, you'll be aware of the recent riots in London, which the government felt had been fueled by Twitter. And their first response was to seek powers to shut down Twitter. And this is in one of the most advanced democracies in the world, so I certainly share your concerns there, Vint. At the back there's a question.
Yeah, the question I had, it kind of came up from the crowdsourcing. And the question is kind of a general disinformation being fed around the web. That's just kind of a common sense thing. And do you guys feel that there's a diffusion of reliable information by a larger production of information? And does that have a kind of a parallel with the mechanics of spectrum and multiplexing?
Okay, so I'm not sure that I heard everything there. Don't worry, the guys will help me if I get screwed up here. One thing I would point out is that the internet is completely neutral when it comes to the quality of information, right? So you can crowdsource good data, you crowdsource bad data, and we've seen how bad data propagates through the network just as quickly as good data does. Is that where he was heading? Or? Okay, so I guess the important point to be made here is that there is no guarantee in the net that when you find something that it's accurate or high quality or not. In fact, the dynamic range is significant. That means that every single person who uses the internet for information gathering needs to exercise critical thinking. I can't imagine a more important thing to teach every kid in the world about information, not just about information on the internet, but all information that they get from all sources, because misinformation can come from books and magazines and movies and television and radio, their friends and their parents, and the internet. And they have to be trained to evaluate the information and try to assess its quality. if they don't do that, then they will be easily misled by information that's wrong.
I can field one part of this. You know, that's I certainly agree, especially in the case of, you know, for example, online news as a resource. You know, any news resource can come from anywhere in the world and be as the New York Times is accessible as some obscure article written by some extremist somewhere. So absolutely, yes. Well, in our case, with the crowdsourcing project that we did, we had to think about how to filter out the noise, right, of all of these inputs. And one way of doing that was to allow it to happen on its own. So each person would look at an image, and they were able to make, at a maximum, 5 contributions independently, randomly given this image. I mean, they can't decide which image to get, not knowing what anybody else had decided to tag, and only were they given feedback after they had completed and submitted their results. So if you're trying to be malicious, or if you don't know what you're talking about, or if you're just really out there, it would dissipate into the noise. But where there was clusters of agreement, where there was amplitudes of consensus, that would spike up and that would show up. So there's also this power to the internet in which it gives us as a populace the ability to make these micro contributions and really directly tap into almost like the vote of each individual person who's tied into the internet. So if there's a way of taking that ability to take those little micro contributions and have consensus and start to make a bigger impact, maybe that's a new way of polling consciousness. Maybe that got a little obscure, but
Joseph.
Thank you. My question is more philosophical than anything else. It's quite clear from the discussions today and yesterday that the internet is becoming this empowering thing. It's almost like having access to language. Once you have it, you can communicate, you can receive information. So as individuals who have a real role in seeing how the internet will progress, and knowing that we live in a world in which societies will never be equal, I mean that's something that's not going to change. Does anyone have any ethical concerns about some individuals having access to sort of 4K high definition video? Well, there are billions of people without access to 100 kilobit per second connections. Is that does that cross anyone's mind at all?
Well, I've seen emerging countries take advantage of the rapid development cycles in wireless to actually upgrade for their own environment much faster than developed countries. For example, you see almost all wireless adaptation and 3G wireless coming to countries where phone lines really were having very slow growth and very expensive growth. Erwin, I'm sure, can talk to that. But I think, as technology develops, all boats raise on the tide. And I think as a technologist, that keeps me going without an ethical concern. If we could contribute to the good and make good engineering advances, I see everyone winning.
So just a statistic or
Just
two.
one comment on the rapidity of the spread into less developed countries. It certainly is happening. And several years ago, we set up a microfinancing project in Indonesia to bring village phones. So we have a box with a phone, an antenna, battery, marketing materials, agreement with the distant cell phone company to share the money with the woman usually that bought the box. And for a short time, that did work quite well. But it began to peter out. Why did it peter out? Because everybody else was buying cell phones. And now it turns out that that's, once you have a place to sleep and a little food, that's the next item that people tend to buy these days. And so that fell through. Interestingly, though, the women in the projects, and a large number of them at the time, had learned to be entrepreneurs. And so then they began to pick up all the other applications, including particularly banking, that were available on the mobile phones. And so this thing still is moving ahead.
I'm going to take a few more questions, sorry, did I cut you off in full stream?
I was only going to mention a statistic or two. In China, you may know that there are 450 million users on the internet. This is coming out of zero, out of nowhere, in a very short amount of time. Of all the countries in the world, that's the largest single population of internet users. The other side of the coin, looking at African statistics, I got very surprised to see that even though there were an estimated 150 million users of internet, presumably with laptops and things like that, there were 350 million people with mobile phones. So once again, this technology of using radio, for which we can thank Mr. Marconi, eliminated the cost of laying fibers and wires and everything else. And its ability to do more economically create connectivity in a wireless way has really been quite dramatic. I can't imagine a more powerful force for development than that.
I'd like to, because we're nearing the end of our time, and there's still a lot of people that want to ask questions, perhaps we should go for a rapid fire question and answer session, give everybody a chance. So any one person that wants to pick up a question, please. So, who's got a question? Over there.
I think the analysis on the traffic growth can be also taken to the perspective of what goes to the core of the network and what goes to the edges. And I think that the numbers might change a little bit. Of course, one of the answers is the development of new technology in the core network and in the wireless access network. But also I wanted to ask probably Vint, how important is the virtual network topology and dynamic networking, pushing the data towards the edges of the network and trying to avoid all of this material, all of this data that might not be useful to everyone to go throughout all the network. How important is that, and how are we going to provide quality of service in a virtual network?
So first observation, if by quality of service you're thinking about the usual metrics of latency and jitter and things like that, is that what you're thinking of? Well, you have to accept the fact that I'm paranoid, or no, I'm schizophrenic on this point. On alternate Tuesdays, I either believe that we have to introduce QoS mechanisms and priority queuing and all this other stuff, and then on the other Tuesday, I come to the conclusion if you just increase the capacity of the system, everything gets better for everybody. And so far, the latter thing has won every single time. So I'm still in the rely on these guys to produce mega bandwidth, and the rest of the problems will solve themselves.
Okay, thank you.
Yeah, I'd like to ask a slightly more technical version of the point Vint Cerf made, which is the Internet of the future going to have central points of government intervention, such as we apparently saw in Egypt? Or will it become more diversified so that it is not possible, even for a government with millions of public safety employees, to shut it down or to heavily restrict it? I mean, China being the other case in point, and even in the US, we made strong efforts in the 90s to limit crypto and strong efforts in the 2000s to limit music and so forth.
Well, actually, you also saw more recently the kill switch business and so on. First of all, let's disambiguate. The Egyptian shutdown was a consequence of shutting down the underlying transmission capability. Packets are not, there's nothing magic about internet. If you don't have any way to transmit the damn packet, it's not going to go anywhere. So fundamentally, they shut down all the underlying important transport capability, although many of us speculated that if that had lasted very much longer, we were going to see radio propagation across the borders, we were going to see satellite capability showing up, a variety of ways to recover using alternative communication tools than the ones that had been offered commercially. So I'm not suggesting that would have been a complete solution, but I think that it would not have persisted in dead silence for very much longer. With regard...
On that, there was also the problem that the economy of the country was crashing. There was so much dependency on having internet available for many things that once you closed it completely, as opposed to try to attack certain things, it had a major impact on
well, you would hope, you would hope that government officials with the capability to cause such a shutdown would also recognize that they were shooting several toes off of their own feet and everyone else's foot as well in the country. So with regard to the intervention of government, which is the other point that you brought up, this is a tremendous tension because I have to accept, maybe you don't, but I have to accept that there are abuses that occur on the net and they're harmful. And they occur not only domestically but across borders. And in order to deal with that, we have to find ways of identifying the perpetrators and doing something about it. So that's going to require at least cooperative measures among governments in order to track down people that do bad things and harm others.
Yeah, maybe there'll be an ITU or equivalent, a Geneva for the internet. I mean, you ever see that happening the way we do?
Well, of course, my biggest nightmare is that the ITU will attempt to assert its authority over this thing. It can't even spell IP, and I hope I haven't insulted anyone here. But I have very strong feelings
That's your
about
hope,
that.
but what do you think will happen?
Yeah. So, I will fight that one to the last packet.
I'd like to ask this one to Bob. Is it easier to shut down the internet because it's carried optically?
Well, you certainly know where the packets are going, so that's certainly true, I think. But at the same time, that core optical infrastructure is used for so much that to shut it down, as Ur was pointing out, I mean, if you shut that down in any large country, it would cripple the country in general. So I think it's true that when you have 100 terabits located in one place, it's much easier to do a lot of damage with an axe. But at the same time, of course, you have diverse routing and so on. And I think that infrastructure is so critical that it has to be protected, it has to be diverse, and hopefully disruptions won't be so frequent.
That's an interesting observation.
Sorry, you didn't mention one thing. This is a new law of physics. I'm announcing it here at the Cal IT2. This is the attraction of an optical fiber generates to backhoes and also boat anchors.
That's not backhaul, that's
Backhoe, that's right. And so that is a big issue. When 3 optical cables were cut in the Eastern Mediterranean and wiped out 80% of the internet and other capacity, we met a couple of weeks later at the request of General Petraeus to talk about alternative capacity by satellite. Diversity really is important in a system like this, especially if we become increasingly dependent on it.
So interesting observation from Bob there,
David?
which is that the damage that's created by shutting down the whole internet to the government itself is something that governments would be reluctant to do. It's an interesting point.
David, there's been a gentleman trying to ask a question here in the center for the start of our panel session.
Is that you, Marty? Go for it.
Two dB per year is 200 decibels in a century, which is a factor of 10 to the 20th. And so while maybe there are things I can't imagine, it seems like there will be some limits to the growth of the internet, although Vince's comment about not just people, but devices talking to each other, sensors talking to each other, will probably keep it going for maybe 50 years, 10 to the 10th. But this leads to another question. I think we may be addressing the wrong issue talking about the internet 100 years out, or even 50 years out. If you go back even 50 years, to 1961, and we had a conference like this, a Marconi Symposium, we wouldn't be asking what is the future of the internet. The best we might be doing is asking, in terms of communications, what is the future of the telephone communications network? We couldn't even envision the internet. And so in some sense, maybe we should be asking the question, what is going to overshadow the internet 50 or 100 years hence in communications, the way the internet has overshadowed the voice network?
So my prediction is if quantum communication works, we won't need the internet anymore because everything will talk to everything in 0 time.
I think personal access to information carried by the internet will create a whole new world where everything we need is there. It's not really a transit issue. We'll be making things localized, and that'll change everything, the way we do things now.
may not have noticed, but the voice network is still with us. I think the point I'm trying to make is that once you get large installations out there, things change very slowly. And I think the same is true of the internet, that huge number of networks connected together. The networks within it may change, backbones will change, but basically we're not going to be seeing major changes. And I kiddingly said last night that perhaps the 100-year prediction is that we finally have transitioned to IPv8.
Question here.
Yeah. So, Vint, you brought up the future of internet governance, right? And I don't know if one can separate that from the future of governance, period. So the question is, will you be able to maintain that separation? Because in the future, internet will be a tool for governance whether you want it or not. And it gives possibilities of creating wealth or stopping riots or creating riots or whatever.
So first of all, I don't believe that you can ignore the governance issues. And in fact, we haven't ignored them. For the last 10 years, there's been the World Summit on the Information Society, the Working Group on Internet Governance, and the Internet Governance Forum, which is about to meet later this month in Nairobi. Governance is going to be important for the Internet. The question will be, what shape does it take, and what does it permit and not permit? And what I hope is possible is to preserve the value of the Internet, which you've been hearing about from all of these people, the ability to share information, to cooperate, to collaborate, while at the same time inhibiting some of the harms that can occur and have occurred using this same medium. So the balance point here is to figure out, first of all, what domestic things can and should be done to protect individuals, and what international agreements are needed, what kind of reciprocity is needed. And it isn't all negative. Let me give you a tiny example. Digital signatures are not necessarily uniformly accepted with authority in every administration. If we had a multilateral agreement about the significance of a digital signature, then there would be a legal framework in which digitally signed contracts could be, disputes arising out of digitally signed contracts could actually be treated in different jurisdictions if there is agreement about the weight of a digital signature compared to a wet one. We don't have such a multilateral agreement right now, and so if you and I engage in a contract and I digitally sign it, and you do as well, and then I breach the contract, you're in Sweden and I'm in the United States, and there's no reciprocity between the two countries, then you may have difficulty having recourse because it isn't the kind of contract for which a legal framework has been established. Those kinds of governance issues are going to have to be dealt with. Copyright is going to have to be dealt with because the ease of digital reproduction and distribution is so great that the classic copyright mechanism which prevents copying, I think, is not going to work too much longer. We'll have to come up with alternative mechanisms. So there's a lot of work to be done in this space. I don't despair. I just think it's a lot of work.
Quickly, do you believe that eventually internet access will become a human right?
I hope not, but let me explain why. Because the sentiment behind it I agree with. But to tie the notion of a human right to a particular technology strikes me as being peculiar at best. It is the right to express oneself that's important. It's the right to hear that expression that's important, not the medium through which it takes place. And so I'm not trying to be argumentative here. What is it my lawyer friends say? Arguendo, for the purpose of having an argument. But I do think it's important that we not bind our thinking about human rights to particular technologies as much as we bind them to the results that we want to preserve.
If you made it a human right, you'd have to give internet to prisoners.
We have time for one last question, if there is one. Wow, I think we finally exhausted you. Okay, well, I think that then brings us to the end of what I hope you will agree has been a fascinating panel session, ranging over a very, very broad range of topics, from the social to the political to the technological, and even to the commercial in some cases. I found it fascinating, so please give our panel a round of applause.